today we're going to do an in-depth look into chemical equations. Some book announcements. Chapter 3 homework, that's due on Sunday, May 31st at 11:59 p.m. I will have office hours on Thursday, 12 to 1:30 p.m. on Blackboard Collaborate, and I'll keep continuing to do that Sunday review session, 8 to 9 p.m. On Blackboard Collaborate as well. Any problems that I work through during that session, I will record those and make those available. So today we're going to start Chapter 4. We're going to look at chemical reactions and how to balance those chemical reactions and how to interpret and understand those chemical reactions with respect to how many moles do I have in the reaction, or how many moles am I expected to get from that reaction. And we'll look at that on a mass basis as well. So you could measure out how much mass I need of my reactants and how much mass would I expect to receive at the end of that reaction. So today is probably one of the most important lectures for the type of material we're looking at and the calculations that we're looking at today. For this semester, and the material we're covering here will carry over into next semester as well. We can interpret a chemical equation in much the same way we interpret a recipe. For example, if you want to bake a loaf of bread, you might want to measure out 2.5 cups of flour, 1.5 cups of water, a teaspoon of salt, a package of yeast, and maybe you're making oatmeal bread, so you mix in 1 cup of oats. So we can all read that and understand what we'd have to do to make that bread, what we would have to measure out and mix together. And we'd also understand if you wanted to make 10 loaves of bread, we would need 10 times the flour, the water, the salt, the yeast, and the oats. A chemical reaction is much the same way. It's going to tell us how much of a material we're putting into the reaction and how much material we'd expect to receive out of the end of that reaction. For example, the reaction here, the combustion of methane gas in the presence of oxygen will produce carbon dioxide and water. And in this reaction, we see that for every 1 methane that I have to put into the reaction, I'm going to need 2 oxygens, and I should expect to produce 1 carbon dioxide and 2 waters during the course of this reaction. We can read this just like we read that recipe and understand if I put in 10 molecules of methane, I would need 10 times the other reagent, and I'd produce 10 times the products as well in this reaction. But first, let's break down the anatomy of a chemical equation. And I've already mentioned reactants and products, but what are they exactly? Right, the reactants, those are the starting materials. That's where I start with this reaction. I'm a material that goes into the reaction. So in the case of baking bread, right, this would be the flour, the water, the yeast. And my products. My products, that would be the final loaf of bread that I make. And in a chemical reaction, the products, that's the material that is produced during the course of the reaction. During the course of the reaction. So in this reaction, I mix 1 methane with 2 oxygens. I'm going to produce 1 carbon dioxide and 2 water molecules as my product. Another important component of a chemical equation, the phase. The phase is going to tell us a little bit more about the physical properties we should expect with my reactants and my products. And will those change during the course of the reaction? So in this case here, I've got methane gas, oxygen gas reacting to produce carbon dioxide gas and water vapor, water in the gas phase. But phase is very important to indicate because it's going to help us determine the physical properties of what we're working with. Are we working with a solid? Am I working with a liquid or a gas? because we know solids, liquids, and gases, all three of the different phases, right, they have different properties associated with them. Another important thing, in this case, the phases stay the same over the course of the reaction, but maybe the phase changes, or you have an unexpected product in a different phase you're not expecting. So the key phases that we will see will be gas phase, and we'll abbreviate that for G, as we saw in the previous reaction. Liquid phase for L, and S is our solid phase. And the last one we've got to mention is the aqueous phase. That's something in solution. So for example, I take solid sodium. I've got solid sodium, and I mix that with chlorine gas, and I'm going to produce solid sodium chloride. What an aqueous reaction would look like would say, maybe I take that solid sodium chloride and I put it in water. So here's my solid sodium chloride. I'm going to mix it with water to produce a sodium cation and a chloride anion, but more importantly, they are aqueous. They are in solution of water now. So ions in solution would be aqueous. So those are the phases we'll come across. And now when we're writing chemical reactions, it's going to be very important to indicate what phase are we working with, because it's going to help us understand, right, the properties of that material. Am I dealing with a solid, a liquid, or a gas, or something in solution? The next two things we need to look at in a reaction are my subscripts and my coefficients. It's very, very important to distinguish between subscripts and coefficients. Subscripts tell us how many of each element are in a molecule. So if I look up at water, H2O, that 2 is a subscript, and that tells me that within one water molecule, I have 2 hydrogen atoms and 1 oxygen. Another example that we've looked at would be glucose, C6H12O6, right? That means I have 6 carbons, 12 hydrogens, and 6 oxygens within a molecule of glucose. So the subscripts tell us within that molecule how many of each element I have there. Another one we could look at would be, say, something like sodium sulfate, Na2SO4. So this subscript 2 applies to the sodium, so that means I have 2 sodiums present, and I have within the sulfate 1 sulfur, and the 4 only applies to the oxygen, so I'd have 4 oxygens present in that sodium sulfate. So subscripts tell us how many elements within a molecule we have. That's different than coefficients. Coefficients, they precede the molecule, and they tell us how many of those molecules do we have in the reaction. So coefficients tell us how many of each molecule we have in the balanced equation. And they precede the molecule in the reaction. So in this case, here's my coefficient of 2. That 2 means I have 2 molecules of water. But when we figure out how many atoms we have, we would see that in 2 water molecules, I would have 2 times 2, I would have 4 hydrogen atoms. And then I would have 2 times 1, I would have 2 oxygen atoms. So coefficients, they go before the molecule. They tell us how many of those molecules I have. And so in the previous reaction we looked at, I've got 1 molecule of methane reacting with 2 molecules of oxygen to produce 1 molecule of carbon dioxide and 2 molecules of water. So when it's the coefficient of 1, we usually do not include that and just assume that if a coefficient's not written, it is 1. I have 1 molecule of methane. So within this 1 molecule of methane, I have, right, 1 carbon, and I would have 4 hydrogens. So we need to be able to differentiate coefficients and subscripts. Subscripts apply to within the molecule. How many of those elements do I have? Coefficients apply to the entire molecule. How many of those molecules do I have in that reaction? So here's an example for you. How many oxygen atoms do I have in magnesium sulfate heptahydrate? How many oxygen molecules do we have in that sample? So to break down that sample, let's look at the magnesium sulfate first. So MgSO4. I break that down. I've got 1 magnesium, I've got 1 sulfur, and I have 4 oxygens. Now let's break down the heptahydrate, the 7 waters. I've got 7 waters. So that means I have 14 hydrogens, and I'm going to have 7 oxygens. So to find out the total number of oxygen in magnesium sulfate heptahydrate, I'm going to add those two together for a total of 11 oxygen atoms in a sample of magnesium sulfate heptahydrate. In the first case, I had to use the subscript 4 to tell me I have 4 oxygens in a sulfate, and in the next case, I had to use the coefficient 7 to tell me I had 7 water molecules, each with 1 oxygen, 7 times 1 being 7 oxygens, for a total of 11 oxygens in magnesium sulfate heptahydrate.